Hello, this is Ken, and we will now be starting with our lesson 1 on units, physical quantities, and vectors. This is a PowerPoint lecture created for the book University Physics 13th edition by Young and Friedman. Most of the examples and figures in this PowerPoint lecture are taken from this book. This will be our goals for this lesson. First, we're going to learn the 3 fundamental quantities of physics and the units to measure them. Next, we're going to understand vectors and scalars and how to add vectors graphically. We will determine vector components and how to use them in calculations. Also, we're going to understand unit vectors and how to use them with components to describe vectors. And lastly, we are going to learn the 2 ways of multiplying your vector quantities. Before we start with our lesson proper, let us first have a brief overview of the nature of physics. Physics is an experimental science in which physicists seek patterns that relate the phenomena of nature. For example, physics aims to explain everyday phenomena like how a ball rolls, or how sound is created, or why metal feels colder than wood even if they are at the same temperature. The patterns that the physicists seek are called physical theories. A very well established or widely used theory is called a physical law or principle. One of the most fundamental laws that we'll be discussing throughout this course are Newton's laws of motion. Physics can be divided into 6 major areas. We have classical mechanics, relativity, thermodynamics, electromagnetism, optics, and quantum mechanics. For this course, we are going to focus our attention on classical mechanics, which is also called Newtonian mechanics. We will now go to our standards and units. In physics, we have 3 fundamental quantities. These are length, time, and mass. We will be using the International System or the SI, which stands for System International, which is the French word, and I'm sorry for that pronunciation, which is the most widely used system of units in describing our fundamental quantities. The SI units are the following. For length, this is measured in meters. For time, in seconds. And mass, in kilograms. These are other fundamental quantities and their units. For example, in temperature, we will use the Kelvin. For electric current, we have the ampere, and for the amount of substance, we usually use the moles. So in this slide are our unit prefixes, which we can add to our fundamental units to signify other range of measurements. Say for example, you have your pico, your nano, your micro, your milli, your centi, your kilo, your mega, your giga. Example, for your meter, you can add the word nano for nanometer, which is equal to a 10 to the negative 9 of a meter. So you have your kilometer. So when you say kilometer, this is equal to the 10 to the third power of a meter. The table here shows some larger and smaller units for fundamental quantities. So we have for length, we have this one as an example on the previous slide. We have 1 nanometer or 1 nm. This is equal to the 10 to the negative 9 of a meter. So a few times the size of the largest atom. A kilometer, for example, or 1 km, this is equal to the 10 to the third power of a meter. For your mass, you have your microgram, which is equal to the 10 to the negative 9 of a kilogram. You have a milligram, which is equal to the 10 to the negative 6 of a kilogram. For our time, we have 1 nanosecond, which is equal to the 10 to the negative 9 of a second. Millisecond, 1 millisecond or 1 ms is equal to 10 to the negative 3 of a second. In physics, we always emphasize inconsistency. So an equation must be dimensionally consistent. Terms to be added and equated must always have the same units. In simple way, be sure you're adding apples to apples. So you cannot simply add a meter to a kilometer, since these are on different ranges, or you cannot add a gram to a kilogram, or a pound to a newton. Stop. So now let us try to review your conversion of units with these conversion examples. We are given here 2 examples for us to practice. First, express 200 cubic feet in cubic meters. So here our target is to convert 200 cubic feet into cubic meters. Okay, so what is this quantity equal to? Okay, so in order to solve this one, we will do a process called your chain link conversion. Okay, it's called the chain link conversion because you will be creating links of multipliers in order to cancel out units to end up with your desired quantity. So let us solve this one. So we write first your quantity that you want to convert on the leftmost um, side of your equation. Okay, and we're going to write out the quantity we're converting as a fraction of units. So we can imagine this one, you have your 200 cubic feet over 1, writing it as a fraction with units. So this is just equal to 200 cubic feet over 1. And then after that, we will cancel out the units, which is here, cubic feet, by multiplying the original quantity by fractions that are equivalent to 1 in a way that the units cancel out. So we are given already with your conversion of 1 foot is equal to 0.305 meters. So we're going to multiply this your 200 cubic feet by this conversion here by writing this one also as a fraction in such a way that we can cancel out your cubic feet here so that we will only be left with your meters unit. Okay, so in order to cancel out this one, we multiply it with the fraction equal to this one. So for us to cancel out the feet, we will write your 1 foot at the bottom of the fraction. Okay, and 1 foot is equal to 0.305 meters. But take note here that this is in cube. You have your 200 cubic feet. So this quantity here should the next quantity should also be in cube. So we are going to cube this one. Okay, so that we can cancel your cubic foot on both sides. Okay, by using your calculator, inputting this one, you have 200 times 0.305 meters cube. Cube this one, cube this quantity here, you will get a value of 5.67 cubic meters. So you can see it for yourselves, try it in your calculators. Next, we proceed with the second example. So here, we are asked to express 75 miles per hour in meters per second. So our target here is to convert 75 miles per hour into meters per second. How much daw your 75 miles per hour in meters per second. So the same process, we do the chain link conversion by writing out first your the quantity that you want to convert on the leftmost side of your equation. You have 75 miles per hour. Okay, so your 75 miles per hour here. And then we use these conversion factors. You have 1 mile is equal to 0.609 meters, and then your 1 hour is equal to 3,600 seconds. So we can write out first your 1 mile is equal to 1609 meters to cancel out the miles, or you can also choose to write first your 1 hour is equal to 3,600 seconds to cancel your hours. So let us multiply this one with a fraction using these conversion factors here. I wanted to cancel out the miles, so I put the miles at the bottom of the fraction. This is equal to 1609 meters. Okay, so here miles can already be cancelled out, and we're only left with the hours to cancel. So to cancel hours, which is at the bottom of the equation, we write 1 hour on top of the fraction, and 1 hour is equal to 300 or 3,600 seconds. Okay, so hours is cancelled, and then you just use your calculator. So you have 75 times 1609 meters over 1 times 3,600 seconds. Solving this one using your calculators, you will get a value equal to 33.5 meters per second. So now let us go to your uncertainty and significant figures. So what is uncertainty and what are significant figures? So the uncertainty of a measured quantity is indicated by its number of significant figures. The number of significant figures is the number of digits about which we have some degree of certainty. Now these are some of the rules in determining the number of significant figures for your quantities. So the first rule is all non-zero digits are significant. So again, all non-zero digits are significant. So say for example, you have 143.44. Okay. Now since this number here contains all non-zero digits, so that means for this number here, we have 5 significant figures. Okay. I believe this is the easiest rule to follow. Next, all zeros between non-zero digits are significant. Again, all zeros between non-zero digits are significant. So let's say you have 23007. Okay, you have 23007. So all the zeros here in between your non-zero digits. So for this example here, we still have, or we have 5 significant figures. Okay, so all zeros or any zero that is in between your non-zero digits, you count it as those are significant zeros. So the third rule is all zeros between the first non-zero digit, which we will call your leading zeros, are not significant. Say for example, you have 0.000321. Okay, you have 0.000321. It says that all zeros before the first non-zero digit. So your first non-zero digit here is 3. So that means these 4 leading zeros here are not significant. So in counting the significant figures for this number here, you only have 3 significant figures. Okay, so any zero that are before your first non-zero digit, looking from your left to right, are not significant. Our fourth rule is in a number with or without a decimal, so again, in a number with or without a decimal point, trailing zeros, those to the right of the last non-zero digit are significant. Again, in a number with or without a decimal point, trailing zeros, those to the right of the last non-zero digit are significant. So everything that is, or all the zeros to the right are significant. So previously, all zeros to the left before your first non-zero digit are not significant. While here, all zeros to the right of your last non-zero digit are significant. So let's say, for example, you have 321,000.000. Okay. So these are already trailing zeros here. Zeros to the right of our last non-zero digit 1. So all the zeros here should be counted as significant. So for this number here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 significant figures. So those are our rules in determining your significant figures for your numbers. So in adding or subtracting quantities, or also in multiplying and dividing quantities, okay, there are also rules involving your significant figures. Okay, so perhaps you have remembered yourselves once during your physics or your math exams, wherein you asked your instructor, like, "Sir, how many significant figures should there be in our final answer?" Well, of course, that is a very wrong question to ask, because you should have already known that there are rules involving those things. Well, if you don't know those things yet, let us go over to those rules here. Okay. So in adding or subtracting quantities, this goes out to your addition and subtraction. So in adding or subtracting quantities, the number of decimal places in the answer should be the same as the least number of decimal places in any of the numbers being added or subtracted. So again, the number of decimal places in the answer should be the same as the least number of decimal places in any of the numbers being added or subtracted. Let's have an example. Let's say I have 3 numbers that I wanted to add. The first number is 143.44, and then the next number is I have 75,231.1234, and then the last number is 1.2. Okay, let us have these 3 numbers here. Okay, now let us add these 3 numbers. According to the rule, the number of decimal places in the final answer should be the same as the least number of decimal places in any of the numbers being added or subtracted. Now let us try to look at these 3 numbers one by one. So your first number, 143.44, this has two decimal places. Okay. You have 2 decimal places here. Your next number, you have 4 decimal places, and then your last number only has 1 decimal place. Okay, now looking at these numbers here, you know now that your final answer should only have how many? 1 decimal places in the final answer. So adding these 3 here, you have 143.44 plus 75,231 0.1234 plus we have 1.2. Okay, let us add this one. So we have 143.44 plus 75231.1234 plus 1.2. If you're going to add that one in your calculator, you will actually get a number of uh, total 75,375.7634. But again, our rule states that the number of decimal places in the answer should be the same as the least number of decimal places in any of the numbers being added or subtracted. We have already determined that your third number has the least number of decimal places, which has only one decimal place. Okay, so here, your final answer should be written as only have 75,375.8. Okay, this is our final answer. So we just round off the number to the right of 7, which is 6, which is greater than 5. So we add 1 to the left. So we have 375.8. Now this is our final answer. Okay, so let us proceed to our next rule. But before that, let me erase these things first. Okay, let me erase this one for a while. Okay, so this time we are going to go through with your addition and multiplication. Okay, in multiplication and division, I mean, okay. So in multiplication and division, the number of significant figures in the answer is the same as the number of significant figures in the input number that has the fewest. Okay, so again, the number of significant figures in the answer or in your final answer is the same as the number of significant figures in the input number that has the fewest. So let us just reuse these three numbers here. You have your 143.44, and then your 75,231.1234, then your 1.2. So your first number, this has five significant figures. Your next number, this has 9 significant figures, and then the last number has 2 significant figures. In multiplying and dividing, our final answer is determined by the number which has the fewest significant figures. So in here, your third number, which has only 2 significant figures, will determine the number of significant figures in our final answer. Since there are only 2 significant figures, your final answer should also have 2 significant figures only. Okay, so let us multiply these three numbers. So we have 143.44 times 75,231.1234 times 1.2. Okay, let's input this one in our calculators. You have 143.44 times 75,231.1234 times 1.2. So by using your calculator, you will actually get a number this large. You have 12949 382.81. Okay, you have that large number. But again, our final answer should only have two significant figures. Okay, so here, since we are only needing two significant figures, you're going to use your scientific notation. Okay, so we only need two significant figures. So for this number here, we can write this one as 1.3 times 10. You have 1, 2, 3, 4, 5, 6, 7. This is 1.3 times 10 to the 7. Okay, let us discuss your scientific notation in the next slide. In the previous slide, you have seen a number which was a result of our multiplication. A number as large as you have 1, 2, or 12,949,382.81. And basing from our rules in multiplying numbers, the final answer should only have two significant figures. However, this is a very large number and it will be very hard to resolve it. So that is why we use the scientific notation to solve our problem. Now, your scientific notation, which is sometimes called the powers of 10 notation, is an easier way of showing significant figures when calculating very large or very small numbers. As an example, you have here 384 million meters. We can write this one as 3.84 times 10 to the 8 meters. So if you've forgotten about your scientific notation, remember that here you have your decimal point at the side here, and then you just move your decimal place to the left. Okay, so let's start. You have 1, 2, 3, 4, 5, 6, 7, 8. So we have moved your decimal places 8 times to the left. So that means you have here 3.84 times 10 to the 8 meters. Going back to our number here, you have 12,949,382.81, and we only wanted to have two significant figures. So from this side here, we move your decimal place to the left. So you have 1, 2, 3, 4, 5, 6, 7. So you can write this one now as 1.3 times 10 to the 7 Okay. So as you have seen here, your 2 was rounded off to 3 because looking at the right side looking to the right of 2, you have 9, which is greater than 5, so you add 1, so you have 1.3 times 10 to the 7. So you have here your 12,949,382.81 written in scientific notation as 1.3 times 10 to the 7. Let us have some comprehension check. The density of a material is equal to its mass divided by its volume. What is the density in kilograms per m cube of a rack of mass 1.80 kilograms and volume of 6 times 10 to the negative 4 m cube? So what do you think is the right answer?